I want you to picture something for a second. Imagine a taxi meter sitting right next to your keyboard.
Oh, man. Just constantly running.
Right, exactly. Every single time you hit enter on an AI tool, every prompt you write, every internal document you ask it to summarize, or like every proprietary line of code you have, it check that meter clicks.
Yeah, you are paying for that intelligence every single time.
And you're actually paying twice. You paying in the subscription fees or the API costs, sure, but you are also paying by handing over your proprietary data, your ideas, and your workflows to somebody else's server.
It really is a meter that just never stops running.
But what if you could just, unplug the meter entirely?
I mean, unplugging that meter changes the entire power dynamic between businesses and cloud providers. We're looking at a fundamental shift in how we interact with, and honestly, how we pay for artificial intelligence.
Well, welcome to today's deep dive. We're looking at a pretty fascinating article from August 2026 by an author named Vinny. It's titled The Frontier on Your Laptop. And okay, let's unpack this, because the implications here go way beyond just saving a few dollars on an API bill.
Right, they really do.
We are talking about fundamentally changing how businesses and individuals structure their software architecture.
Yeah, and our mission for you today is to really explore how the rapid rise of local AI capabilities is completely rewriting the economics of this technology. Specifically, we're looking at open weight models that you can run right on the laptop sitting in front of you right now.
Which, I mean, it sounds almost like science fiction compared to where we were just a couple of years ago.
Oh, totally.
We are just so used to the idea that real AI happens in some massive glowing data center in the cloud, right? Like consuming the power of a small city.
Exactly. And we really need to set the narrative anchor early on here, because a lot of people just completely misunderstand this shift. This is not a story about local AI, quote unquote, killing cloud AI.
Right, the cloud isn't going anywhere.
No, the massive cloud models aren't going anywhere. Instead, this is a story about a massive shift in how we route our cognitive workloads. It's about having the capability to choose where the computational thinking actually happens based on the specific task at hand.
That concept of routing perfectly sets up the shifting baseline of AI economics. To understand why we're talking about routing instead of, replacing, we really have to look at what happened earlier in 2026.
Yeah, that was huge.
Google dropped an absolute game changer, the release of Gemma 4, and specifically its 12 billion parameter sibling.
That release fundamentally altered the baseline of what developers expect from local hardware.
It really did. Because look, this is a model built on the exact same research and technology as Google's massive Gemini 3 model. But the kicker is the size you can download it, as a 7.6 gigabyte artifact.
Which is wild when you think about it.
It is. To put that in perspective for the professionals listening, 7.6 gigabytes is roughly the size of a few heavy Docker containers, or like a loaded node modules folder.
Yeah, we've all seen those.
Right. A model from a Frontier Labs research line can now just sit comfortably on a standard developer's laptop.
What's fascinating here is the dual economic shift playing out simultaneously. On one side of the equation, hosted inference berries. The cloud AI we've all been using keeps getting cheaper.
Right, prices are dropping.
Yeah, the massive providers are constantly dropping their prices per token as they optimize their data centers. But on the other side of the equation, the local capability floor keeps rising. The baseline of what you can accomplish for free on your own machine is just getting incredibly high.
But I'm stuck on the cost argument, though. If cloud providers are dropping their API costs to fractions of a penny per 1,000 tokens, the hassle of downloading, configuring, and, running models locally hardly seems worth it.
I get why you'd think that.
I mean, why not just let the cloud handle it if it's practically free?
Well, because practically free is not free, especially at scale. The source is very clear about this. A local model like Gemma 412B is not the closed frontier in miniature.
Right, it's not a supercomputer.
Exactly. It's not going to invent a new chemical compound from scratch. But it has now crossed the quality threshold for high-volume bounded tasks. Think about tasks like formatting thousands of rows of data, summarizing endless meeting transcripts, or doing basic repetitive code review.
The kind of tasks where you are processing millions of tokens a day.
Precisely. When a local model can handle those everyday tasks flawlessly, the marginal vendor charge for those specific workloads drops to exactly zero.
Wow.
And zero scales infinitely better than fractions of a penny. When the cost for everyday tasks drops to zero, it completely flips the burden of proof onto the premium cloud models.
Right, it changes the whole conversation.
It does. The strategic question for a business is no longer, Can we afford to use AI for this task? The question becomes, does this specific task actually require the premium expensive cloud model, or can our local machine handle it for zero marginal cost?
So it is entirely about triage. If the economics are pushing us to pull these high-volume tasks in-house, we need to clarify what exactly it is we are bringing inside the corporate firewall.
Yes, because the terminology gets really confusing.
It gets incredibly messy. The author is very careful to use the term open weight instead of open source.
Yeah, the phrase open source gets thrown around constantly, but in the context of these AI models, it is almost always technically incorrect.
Let's break down that mechanism for a second. When you download a model like Gemma 4, you are getting the open weights. You are getting the billions of trained parameters, the massive mathematical matrix that makes the neural network function.
Right. The actual brain of it.
Exactly. You get to run it on your own hardware and you can fine-tune it, but you do not get the original training data. You don't get the full training code. You don't get the complete recipe of how they baked the cake. You just get the finished cake.
And that distinction is absolutely paramount for lawyers, compliance officers, and regulators.
Why is that?
Well, if you are making commitments to a corporate board or to a healthcare customer or a government regulator about the software supply chain you're using, you have to know what rights you actually possess. Because you don't have the source data, you cannot perfectly audit the model for biases.
Yeah.
Or for copyrighted material, or vulnerabilities the way you could with traditional line-by-line open source software.
So if it isn't traditional open source, how are the creators of these models structuring the legal agreements?
We are seeing a major shift toward permissive licenses, which provides much-needed clarity for businesses. Apache 2.0 is really becoming the standard here.
Okay, so who's using that?
Gemma 4 uses it, as do Qwen 3, Mistral 3, and GPTOS. Apache 2.0 permits commercial use, modification, and redistribution, and crucially, it includes express patent terms. You also have models like DeepSeek R1 utilizing the MIT license, which is similarly permissive.
But then you have Meta's Llama 4, which takes a wildly different approach to licensing.
Yeah, Meta uses a highly customized license for Llama 4. It requires a specific built-with Llama attribution if you distribute a product based on it.
Okay, that's not too bad.
But more importantly, if your organization surpasses 700 million monthly active users, you must go back to Meta and request a separate, potentially paid license.
I can hear startups listening right now thinking, having 700 million users is a problem I would love to have.
Right. It sounds like a good problem.
But from a systems architecture standpoint, that is a massive hidden tripwire. If you build your entire core product around Llama 4 and you hit that growth curve, Meta suddenly has massive leverage over your business model.
Exactly. It introduces an existential risk to your architecture. The overarching takeaway isn't that you can bypass your legal team. I mean, legal review is always mandatory.
Of course.
But permissive licenses like Apache 2.0 simply make the terms static and predictable. You know exactly where the boundaries are, and they won't suddenly shift based on your success.
So once the legal team gives the green light on an Apache 2.0 model, the immediate bottleneck becomes the hardware. Like, where do we actually put a model of this size?
That's the million-dollar question.
I was thinking about the deployment map discussed in the article, and it reminds me of how a professional kitchen routes its prep work versus its main courses.
Oh, I love that. How does that map to the hardware infrastructure?
Well, at one end of the map, you have the massive commercial kitchen setup. Think of a model like Llama 4 Scout. The text notes, this is a 109 billion parameter beast.
Huge.
Yeah. Even running its most efficient version requires an NVIDIA H100 data center GPU. That is a commercial pizza oven. You do not install that in your home kitchen.
No, you definitely don't.
It requires massive power, specialized cooling, dedicated infrastructure. When you use an API, you're basically renting space in someone else's commercial kitchen.
And paying a premium for that access, yeah.
Yeah, exactly. But at the other end of the deployment map, you have the high-end commercial microwave. That is your Gemma 412B. It fits on the laptop you already own. You don't fire up the massive industrial pizza oven just to melt a stick of butter, right?
Right. That would be ridiculous.
In the same way, you shouldn't ping a massive cloud model just to reformat a CSV file. You route the small, high-volume prep work to the microwave on your desk.
That perfectly illustrates the mechanics of routing workloads.
Yeah.
By keeping that prep work local, using the microwave on your desk, you unlock massive advantages for a business's AI ledger. The author actually details 3 specific structural shifts here.
Let's go through those. We already covered the first one, right?
Yes, routing economics, where the vendor charge drops to 0. But the second shift is arguably even more important for enterprise listeners, and that's Data gravity.
Data gravity usually dictates that moving massive amounts of information is expensive and risky, so applications tend to be pulled toward wherever the data lives. But in the cloud AI era, we've been forced to reverse that.
Yeah, we're doing the exact opposite.
We've been sending our most sensitive proprietary data out to a hosted endpoint.
But with self-hosted open weights, you restore the natural law of data gravity. You bring the model directly to your data. If you operate in a regulated industry like finance, defense, or healthcare, this changes everything.
It really does.
It drastically simplifies data residency and compliance reviews. If the proprietary data never physically leaves your company's laptops or internal servers, the risk of a third-party cloud provider intercepting it or suffering a breach is literally eliminated.
The author does issue a strong caveat there, though. Keeping the data local doesn't magically solve all your security problems.
Oh, far from it. Local is merely a deployment property. Approved and secure is a governance outcome. You still have to manage access control. You still have to manage identity verification.
You still have to do the work.
Exactly. You still have to defend against software supply chain attacks. The model is running inside your walls, but you still have to lock the doors to the building.
And if the data stays secure inside the building, that leads directly into the third structural shift, the learning loop. The author references a concept from Microsoft CEO Satya Nadella regarding learning exhaust.
Yes, learning exhaust.
Think about your own workday. Every time you use an AI tool, you provide context. You paste in internal memos, you correct the AI when it hallucinates a line of code, you refine your prompts. All of that interaction is learning exhaust.
And in a cloud-based model, the vendor absorbs that exhaust. They use your corrections and your context to quietly improve their overarching model. You are effectively paying them for the privilege of doing their QA testing.
Which is wild when you say it out loud.
It is. But by self-hosting an open-weight model, you capture and own that learning loop. Your context, your corrections, and your specific workflows stay internal. They act as a competitive moat rather than free training data for a vendor.
Okay. So what does this all mean? We have zero marginal cost for everyday tasks, we maintain total data privacy through data gravity, and we capture our own proprietary learning exhaust.
That's pretty good, right?
It sounds incredibly tempting to just sever the cloud connection entirely and move every single workload locally, but we have to do a reality check here. You can't cook a 5-course gourmet meal in a microwave. Self-hosting is never truly free.
No, it's not. The hidden infrastructure and maintenance costs are substantial. The article explicitly details the expenses of raw compute GPUs, the electricity to run them constantly, rigorous security reviews, patch management, system observability.
The list goes on.
Yeah, and undoubtedly the most expensive line item, the highly skilled human engineers required to maintain all of it.
We also have to acknowledge the hard capability limits. A 12 billion parameter model is incredibly useful, but it is fundamentally constrained. The text notes that to run efficiently on a laptop, these models are often quantized.
Yeah, quantization is the physical reality check of local AI.
Yeah.
To fit a massive neural network onto a standard laptop's memory, you have to mathematically compress the precision of the model's weights.
Right. Squeezing it down.
Exactly, often crunching them down to 4-bit integers. You save a massive amount of memory, but you inevitably lose some fidelity and reasoning capability in the process. A quantized 12 billion parameter model simply cannot execute complex, multi-step, autonomous agentic workflows. That hard, long horizon work still belongs in the cloud.
Knowing those limits, how does an engineering team actually decide what gets routed where?
Well, you implement what the author calls an evaluation portfolio. You cannot rely on vibes or generic guesses to determine if a local model is sufficient. You establish strict, measurable pass conditions for your specific internal tasks.
What does that look like in practice?
So if you needed to extract action items from meeting notes, you run 1,000 test transcripts. Does it capture every action item accurately? If it passes your internal quantitative tests, you route that workflow locally. If it hallucinates or fails, you route it to the premium cloud model. Measurement replaces guesswork.
Speaking of physical limits and measurement, the text points out a technical limitation with the llama that confused me a bit.
Oh, about the context windows.
Yeah. It mentions that Gemma 4 features a massive 256K context window, meaning you could theoretically feed it hundreds of pages of text at once. But the author warns that this 256K number is just a ceiling, not a guarantee. If the model is built to handle 256K, why wouldn't I always get access to that full window?
Because context windows are not abstract concepts. They physically take up space in your hardware's memory. The attention mechanism in a neural network scales quadratically.
Meaning it gets exponentially heavier.
Exactly. The more text you feed it, the more active memory it requires to keep track of how all those words relate to each other. A llama dynamically allocates your context window based on the physical VRAM, the video memory, available on your specific machine.
So the software looks your hardware and throttles the capability.
Yes, it has.
If your laptop has less than 24 gigabytes of memory, a llama restricts the context window to just 4K. If you have between 24 and 48 gigabytes, you get 32K. You only unlock that massive 256K window if your machine has 48 gigabytes of RAM or more. Context literally eats memory.
It really does.
If you try to force a 100-page architectural document into a laptop with only 16 gigs of RAM, the system will simply fail to process it.
And that physical constraint is precisely why the author insists that reading white papers about local AI isn't enough.
Yeah.
You have to physically hit those limits yourself to understand where the capability floor actually sits.
Well, here's where it gets really interesting. The author provides a 15-minute calibration experiment that you, listening right now, can run today to feel these mechanics firsthand. The barrier to entry is shockingly low.
It requires no specialized back-end engineering knowledge at all.
Let's walk through the setup. The author uses an Apple Silicon Mac, which is a standard environment for many professionals. You need a minimum of 16 gigabytes of unified memory, though the text strongly recommends 32 gigabytes.
Yeah, you want some breathing room.
Right. You want to leave enough physical memory for your operating system, your web browser, and your IDE to function while the AI is simultaneously monopolizing resources to think.
So you go to Walla.com, download the installer, and open your command terminal. You type one simple command, and it pulls down that 7.6 gigabyte Gemma 4 12B model. A llama automatically handles the complex backend mechanics.
That's super convenient.
It is. It handles the chat templates, managing the context windows we just discussed, and applying Google's recommended defaults for temperature and sampling.
And once that model is downloaded and running in your terminal, the author suggests a brilliant final step. The Wi-Fi test. You physically disconnect your computer from the Wi-Fi, turn off your internet entirely, sever the connection to the cloud, and then you ask the model to do real work.
The isolation of that test is profound. When you see a model generating complex code or summarizing text while entirely offline, you get blunt, undeniable confirmation that the computational thinking is happening strictly on the silicon sitting on your desk.
It is a visceral feeling of control, but you have to test it with actual difficult work. Generic prompts like, write a poem about a software engineer, teach you absolutely nothing about the model's utility for your business.
No, they really don't.
Take a dense, convoluted PDF from your actual work week and ask it to summarize the unresolved risk factors. Or hand it a chunk of unfamiliar, messy code and ask it to explain where a memory leak might occur. Because Gemma 4 12B is multimodal, you can even drag and drop a complex architectural diagram into the prompt and ask it to explain the data flow.
But you must keep its isolation in mind while evaluating the output. This specific model has a training data cutoff of January 2025. Because your Wi-Fi is disabled, it has no search engine access.
So it's completely cut off from the present.
Exactly. It knows absolutely nothing about the news this morning or a software framework released last week. It is relying 100% on the weights it was trained on and the specific context you provide in the prompt.
It forces you to become a better operator. You have to provide all the necessary context yourself. But when you do, and you watch it successfully debug a script or summarize a proprietary document while completely disconnected from the outside world, it fundamentally shifts your perspective on what a personal computer is capable of. Synthesizing the core message from the text here. Completing this 15-minute calibration permanently changes your negotiating posture. When you read your next API bill from a cloud provider, or when you are sitting in a meeting discussing data compliance, you are going to approach the problem differently.
You have leverage now.
You do. You have met the local alternative firsthand. You understand exactly which high-volume tasks you are currently paying for that you could be executing locally for zero marginal cost and zero data risk.
It takes the abstract concept of an AI portfolio and makes it tangible. For you listening right now, whether you are prepping for a quarterly budget meeting, leading a team of developers, or you are simply fiercely protective of your proprietary data, understanding this shift is incredibly empowering.
It absolutely is.
Knowing how to intelligently route your cognitive workloads between the massive cloud models and your own local device puts you firmly back in the driver's seat. You control the budget, you manage the privacy, you own the learning loop. And if we connect all of these mechanics to the bigger picture, It raises an important question that builds directly on the implications of the text. If our local machines are suddenly capable of handling our most sensitive, high-volume cognitive tasks entirely isolated from the cloud, how will this shift in data gravity alter the very nature of the hardware we purchase?
That's a great point.
Think about it. In a few years, will we completely stop caring about processor speed and instead view massive amounts of physical RAM as the ultimate currency of personal privacy and professional independence?
Because if context eats memory, then whoever holds the most RAM gets to keep the most secrets. Take 15 minutes today, unplug the meter, and run the test. Thank you for joining us on this deep dive.